This lecture is part 2 for the topic on uniform flow in open channels. In an open channel, even in a simple one, the roughness in the channel bed may differ with the one on the side walls. Hence, it is important to have methods or way to compute this representative roughness or equivalent roughness for the whole section. For determining this equivalent roughness, the water area is divided into imaginatively n parts, of which the weighted parameters and also the roughness coefficients are known. Several authors have proposed several types of formula to compute this equivalent roughness, meaning n. For example, the equation by Horton and Einstein, Pavlovsky, and also Lotter. This example shows how we can calculate this equivalent roughness for a trapezoidal shaped channel that have different roughness coefficient between the channel bed and the side wall. So, a trapezoidal channel with sides 1 to 1 and bed slope 1 to 1000 has a 3 meter wide bed composed of sand with n equal to 0.02 and sides of concrete with n 0.014. You are to estimate the discharge when the depth of flow is 2 meters. So, to solve this problem, we need to divide the channel into different parts according to their roughness. For this trapezoidal shaped channel, we can divide it into 3 parts. One part for the sidewall on the left, the second part is for the channel bottom, and the third part is for the sidewall on the right. But since this is a trapezoidal shape which is symmetrical, the part for the sidewall on the left will be equivalent to the part for the sidewall on the right. So from there, we can actually calculate the weighted parameter. In this case, P1, which is for the side wall on the left, should be equal to P3 for the side wall on the right. It will be equal to 2.828 meter. While P2 here is actually the weighted parameter for the bottom channel itself, which is 3 meter. So if we total this up, we will get the total weighted parameter as 8.656 meter. Same case for the area. We need to find the area for the left side wall, which is equivalent to the area for the right side wall. So A1 will be equal to A3 equal to 2 meters square, while the area which the channel bottom represent is A2. In this case, because the floor depth just now is 2 meter and the width of the bottom is 3, so 3 multiplied by 2 will get you as 6 meters square. Total area will be 10 meters square. For the hydraulic radius, it will be A over P. In this case, the hydraulic radius for the left side wall is equivalent to the right side wall. So R1 equal to R3 equal to 0.7072 meter. While for the bottom channel, the R2 is 2 meter, and then the total of this hydraulic radius is 1.155 meter. So having calculated all this value, then we can input this value into the respective equations. So for the purpose of this example, it shows the calculation for the representative or equivalent roughness using the 3 different types of equations. You can also just choose one which you feel that is suitable for the channel. So like in this case, if we use the Horton and Einstein equation, it will get you the N will be equal to 0.0162. For the Pravorsky, the N is actually equal to 0.0163, while for Lotter, the N is 0.0157. For all of these equations here, it actually involves the summation, either multiply the P with the N and then divide by the P. For example, like the Horton and Einstein equation, on the top of the equation is actually summation of P I Ni power 1 over 5 divided by P power 2 third. In other words, this means that for the top part, you multiply P1 with N1 to the power of 1.5 plus P2 multiplied by N2 to the power of 1.5 plus P3 multiplied by N3 to the power of 1.5 divide by the total P, then the whole calculation you power it as 2 over 3, it will get you as 0.0162. For the Pravorsky, it's actually the summation of P1 multiplied by N1 square plus P2 multiplied by N2 square plus P3 multiplied by N3 square divided by the total P to the power of 1 over 2. While for the Lotter, given in the question is P r to the power of 5 over 3, or in other words, the upper part of the equation is you get the total P multiplied by the total r power of 5 over 3, then divide the lower half is the summations for the three parts, namely P1 R1 to the power of 5 over 3 divided by N1 plus P2 R2 to the power of 5 over 3 divided by N2 plus P3 R3 to the power of 5 over 3 divided by N3. So all of this will get you as 0.0157. Then you apply the Manning's equation. Q equal to 1 over N A R to the power of 2/3 multiplied by square root of S. So by using the different value of N from these three equations, you'll find that the discharge varies not that much, just a little bit. So for example, from Horton will get you the Q as 21.49 meter cube per second. Pravorsky is 21.36 meter cube per second, while for Lotter is 22.17 meter cube per second. Next, we're going to look into design of channel. In this case, we will only be focusing on design of non-erodible channel. Non-erodible channel here means that the channel are not subjected to erosion, meaning the channel have an immovable back and side wall. So in order to design this channel, there's a few things that need to take into account when it comes to this design. For example, the kind of material for the channel body, the minimum permissible velocity, this is to avoid deposition of sediment, the channel bottom slope and side slope, the freeboard, and the most efficient section, either hydraulically or empirically determined. For non-erodible channel, the material that can be used are such as concrete, stone masonry, steel, cast iron, timber, glass, and plastic. Normally, the selection of this material will depend on the availability and also the cost of the material. In terms of the minimum permissible velocity, this minimum permissible velocity will prevent siltation to happen in the channel, which can induce growth of aquatic plant and moss. The mean velocity that is generally recommended is 0.6 meter per second. For the channel slopes, the longitudinal bottom slope of a channel is generally governed by the topography and the energy head required for the flow of the water. The side slopes of a channel depends mainly on the kind of the material. Freeboard of a channel is the vertical distance from the top of the channel to the water surface at the design condition. This extra vertical distance is required to prevent overspill of the flow due to waves or fluctuation of the water surface. According to the Bureau of Reclamation, it recommends to use the following formula for the freeboard, which is F equal to square root of CY. F here is the freeboard, but in this case the unit is feet. Y is the depth of the water in the channel, and C is the coefficient, which varies between 1.5 for a discharge of 20 cubic feet per second to 2.5 for a discharge of 3000 cubic feet per second. So by using this equation, the US Bureau of Reclamation prepared curves to determine this average freeboard. This chart, as developed by the US Bureau of Reclamation, can be used to determine what is the required freeboard for your channel. But of course, if you're using SI unit, you need to do conversion of unit first before you can use this chart. To use this chart, first you need to determine what is the discharge or Q required by the channel that you are designing to carry. Once you know this Q, you can go to the horizontal axis of the chart to the appropriate value of your Q just now and pull a vertical line up until touching the curve on the chart. And then from there, you can pull a horizontal line and read on the vertical axis what is the required freeboard. The next thing that need to be considered in design of channel is the best hydraulic section. In the viewpoint of hydraulic, the best hydraulic section is the section having the least weighted perimeter for a given area and gives the most maximum conveyance or discharge. The semicircle has the least perimeter among all the sections with the same area, hence it is the most hydraulically efficient of all sections. To determine this best hydraulic section, we can use the proposed equations for different shapes as listed in table 1. So in this table here, it shows how to calculate the most efficient section for channel shape of rectangle, trapezoidal, circular, and triangle with the appropriate A, which is the cross-sectional area, weighted perimeter P, the bottom width B, the height radius R, and the top width T. For trapezoidal shape, the optimum value of side slope M is given as 1 over square root of 3. So, from the previous considerations that we have seen from the previous slides, we can summarize that to design an open channel, it will follow the following steps. The first one is to collect all necessary information, and from this information, it will help you to estimate what are the roughness and also the slope. These informations may include what are the material for the channel and also the topology of the location where the channel will be designed so as to determine the suitable slope. Then the next step is to compute the section factor AR power 2/3, solve the above equation for the depth. If there are other unknowns such as the bottom width B and Z for a trapezoidal section, then assume the values for this unknown and solve it using the Manning equation. If the best section is required directly, substitute in Manning equation the expression of the area and the hydraulic radius obtained from the previous table for the best hydraulic section and solve for the depth. Then we need to check whether the velocity is follow the minimum permissible velocity requirement so that the water can carry the sediment or siltation. And finally, add a proper freeboard to the depth of the channel section. Let us take a look at this example on how to design the most efficient channel section for a trapezoidal shaped open channel. A slightly rough brick line trapezoidal channel carrying a discharge of 25 meter cube per second, there's a typo error there, is to have a longitudinal slope of 0.0004. Analyze the proportions of the most efficient channel section of trapezoidal shape, assuming the Manning's roughness n equal to 0.0017. For the most efficient trapezoidal channel section, we can refer to the table just now to get the appropriate properties. For the side slope, m is given as 1 divided by square root of 3, which will get you as 0.57735. As for the cross-sectional area A, as given in the table, it is equal to 1.732 y squared, and the r is y divided by 2. Then we can substitute this value into the Manning equation. Q equal to 1 over n AR power 2 over 3 multiplied by square root of S. Since in the question, it did give you the discharge, the Manning's roughness value, and also the slope, then we can simplify that equation so that you will get it in terms of the y. And in this case, it will give you y power 8 over 3 equal to 19.4753, which will give you y as 3.045 meter. And finally, the bottom width will be equal to 2 divided by square root of 3 multiplied by the y, which is 3.045, which will give you as 3.516 meter. With that, we end the topic on uniform flow in open channel. Thank you.